All right, we can make alkyl halides from radical reactions in addition. So remember, we've talked about this before. Radicals can do substitution and addition. We'll talk about those in a second. And the chain reactions, right? 3 steps. So if we're drawing a mechanism for radical substitution or radical addition, you want to show initiation, propagation, termination. Remember, in initiation, you make radicals. In propagation, you react and you use radicals and you make radicals. And then finally, in termination, you use up radicals. They react to go away. So we saw this with radical substitution. So Cl2Br2, light or heat, right, to activate it, we can do a substitution reaction, right? We're removing a hydrogen and replacing it with a chlorine. And if I did the mechanism, it would be something like this. Remember, I'm going to use light here. Remember, fish hooks for electrons, for radicals, right? We're showing each electron move. So propagation step, I would have 2 steps. The chlorine radical I made is now going to react with my alkane, right? And radicals like to abstract hydrogens. So 3 arrows in this case, right? I'm taking the 2 electrons in the CH bond and the 1 electron from chlorine, reacting. Next step, the radical I made reacts with another equivalent of ClCl. And so that makes a Cl dot and a Cl, the product. So this is the substitution product is done. We made both our products, and then finally termination steps. I would draw Cl dot could react with Cl dot to make ClCl. Cl dot could react with the alkyl radical to form one more product, or the alkyl radical could react with the alkyl radical to form this guy. All right, so 3 termination steps. And again, remember what's happening here is you are generating radicals. You're using those radicals, right? You have to have a radical in every step in propagation. And then finally, when those radicals start reacting with each other, you start losing them from that pool, and the reaction slows down and eventually stops. All right, so we know radical substitution. That should be a review. You should be able to draw this arrow mechanism, initiation, propagation, termination, for radical substitution reactions. We also did this kind of problem, right? Predict all possible monochlorinated products for the following. So, right, I'm just looking at different hydrogens that I can do substitution to. So remember, when you do this, I could go here. I could substitute a hydrogen here, the primary hydrogen. I could substitute at the tertiary position. I could substitute at the secondary position. I could do substitution at this secondary position. And I could do substitution at this secondary position. The other 2 are the same, unless we're considering stereochemistry, because really this guy's going to give me a pair of enantiomers probably. This guy's going to give me a pair of enantiomers. And none of the others are chiral. Okay, so predicting all possible, you have to look and identify all the different hydrogens, right? And so usually we don't use radical substitution for synthesis, right? You can halogenate in different positions, and you can multiply halogenate. So if this guy was the substrate, for the next reaction, I'd put a chlorine here and maybe a chlorine here, right? So you have to watch out for the multiple halogenations, chlorinations, okay? Radical addition, we've seen. Remember, so this is the anti-Markovnikov. We make the anti-Markovnikov product. It goes through a radical intermediate. And remember, in this mechanism, you should be able to draw the entire mechanism out. But the important step is this one, where this guy adds here to get the tertiary radical, rather than if bromine adds here, the radical would be here, right? And that would be a secondary radical, less stable. So this is where we're going, right? 2 choices, and because bromine adds first and you get the radical intermediate, right, you want to have the more stable radical intermediate, and that's why we get the anti-Markovnikov alkyl halide. More review. All right, some kind of new stuff. So here, predict all the products for this radical substitution reaction, right? I can substitute at the tertiary position or the primary position. thing we want to think about here is which is more reactive, which position is more reactive. So if I do this reaction, not me, but somebody who can do organic synthesis, does this reaction and measures how much of each product you get, turns out you get 35% of the tertiary and 65% of the primary. So that suggests that the primary position is more reactive, right? You have more of that product. But this is kind of cool. You have to consider how many ways you can make these products. How many tertiary hydrogens are there? There's only one. So if I take 35 and I divide by the one chance, it's still 35%. If I take the 65 and I divide by how many hydrogens do I have, how many primary hydrogens do we have in this guy? 1, 2, 3, 4, 5, 6, 7, 8, 9. So he has 9 chances, right? So if you're gambling, you have a better chance of finding a primary than you do of a tertiary. So we have to account for that. All right, so 65 divided by 9 is 7.2. All right, so these are the relative ratios of these two things. So it's still 35, but now this guy's only 7.2%, I guess, right? And so if we took this and 35 divided by 7, we get 5 times. So the tertiary position is 5 times more reactive than the secondary position. And if you do this again, you can find out that, where are my other numbers? Where's my numbers? I think it's 3.5. Where is that? It's missing. Anyway, I think what you get is that the tertiary is 5 times faster. And I think it's 3.5 times and then 1 time. So tertiary is the fastest, or the fastest formed, the most easily formed. All right, for chlorination. Let's see. And why is that? It has to do with the radical stability, right? In the mechanism, right? The rate limiting step is the formation of a radical, right? And different radicals have different stabilities, just like carbocations. So as expected, maybe, well, this is actually reversed. Methyl vinyl, then primary, secondary, tertiary. The more substituted the radical, the more stable it is. So this is very similar to carbocation stability. You can use bond dissociation energies to figure this out. So if I take different substrates, right, and I measure the energy required to remove those hydrogens. So here's a vinyl hydrogen. The energy is 445 kilojoules, right? Should we draw this? Does this help? So 445 to get up here, right, to get the vinyl radical. And let's use tertiary. If we get the tertiary, what do we get? It's only 390 from there to there. So we know that the tertiary radical is much more stable than the vinyl. So we see primary is less stable than secondary, tertiary. The resonance has a bigger effect. But resonance and hyperconjugation are both things that affect this. So hyperconjugation, remember, this is the resonance, this is the stabilization of the radical by adjacent CH bonds, right? The electrons in those sigma bonds next door. And we also have resonance. So there's 2 different effects that stabilize radicals. Hyperconjugation, when you have adjacent CH bonds, and resonance, right? So we can draw resonance for this allyl radical. All right, so if we look, this will be fun. Hyperconjugation, so this guy is stabilized by hyperconjugation, hyperconjugation, hyperconjugation. These ones aren't. And then these guys are resonance stabilized, right? So 2 different stabilization effects. All right, so chlorination is, if you compare this to carbocation stability, one difference you'll see is that primary, secondary, benzyl, and then tertiary. Tertiary is the most stable, right, in terms of carbocations. Tertiary is a little less stable than allyl and benzyl in the radicals. So allyl benzyl radicals, resonance stabilization seems to be more stabilizing for radicals than for carbocations. All right, so chlorination is not that useful, right? 5 times faster at the tertiary versus 3.5 to 1 at the primary. Let's do the same analysis, but for the bromination. So radical bromination, you do this analysis, you measure up what you make, and you get 99% of the tertiary. and only 1% of the primary. So now this is much more selective, right? And organic chemists love selective reactions. That means, right, we have a major product, right? This is definitely major. This is definitely minor. A little purification step, and we've purified this guy, right? And that excites organic chemists. And the reason for this is, if we draw the energy diagram, right, if we look at this first step where the radical abstracts the hydrogen, the first step for the bromination is endothermic. So you make the tertiary radical in this case, and then HBr. Should we go red? Probably should. It turns out for chlorination, the first step is exothermic. So you get this guy. Right, and so it turns out that this is plus 24 kilojoules, not to scale, bad work by me, negative 42 kilojoules. All right, so the bromination step is slower, being endothermic, and we can consider that Hammond plays a part now, right? So we can say that because this tertiary radical is formed in this endothermic reaction, this transition state is going to look more like him, and anything that stabilizes that is going to have an effect. So if I put a primary substrate on here, well, I can do this guy, right? He's going to be that much higher, right? And so because we know the relative stabilities of the primary radical versus the tertiary, we're able to predict that these transition states will be similar in energy, and so it'll be slower. So the tertiary should form faster than the primary. So again, right, George Hammond allows us to relate thermodynamics, right, the stability of intermediates in endothermic reactions, to the rate of the reaction. Whereas at the exothermic, this guy doesn't really look like him, and so you can't say anything about that transition state, right? If I have a less stable one here, who knows what effect? It doesn't have a very much effect on the transition state, right? And so slower reactions are more selective, and in this case then, bromination is useful. Oh, no. All right. One more thing to talk about then. So here are our bromination reactions. So HBr and an alkene, we know we make the Markovnikov alkyl halide. Br2, right, halogenation, we get the anti-addition, right? We get a pair of enantiomers in here through the bromonium intermediate. A new one we're going to add is this NBS and light. CCl4 is a solvent, it may be there or not. But this is a reaction called allylic bromination. And what we're going to see is that the major product is bromination at this position. Remember, that's the allylic position when you are on a carbon attached to a double bond, right? This guy is vinyl. These guys are vinyl. This guy is allylic. And so if you do this radical substitution reaction with dilute bromine, right, and it's important that the Br2 concentration is dilute, otherwise this guy competes, right? What you get is allylic substitution. Let's see, so how do we generate our Br radical? We use this reagent called N-bromosuccinimide, NBS. And what happens is it slowly releases bromine, and then in the presence of light, that becomes the radical. So this is just NBS is a really dilute source of bromine. Right, and why is it important? Right, we want to do the radical reaction. If we have high concentrations of Br2, we're going to do the addition reaction. Right. Why is the allylic reaction so selective? Let's look at the energies. So the secondary, this would be secondary allyl, and this guy would be vinyl. And so what numbers do we have here from our table? Vinyl is 445 kilojoules. Secondary, or allyl, is going to be less than 361 in this case because it's secondary allyl, even more stable than this one, 401 kilojoules. So this is much more stable, or easier to break, right? So the allyl radical is more stable. Remember, Hammond says it'll form faster, and we'll get our product that way. All right, so predicting products, we, NBS and light, we recognize. Come on, thing. We're going to do allylic substitution. All right, so I substitute a hydrogen with a bromine. There we go. All right. KOH here, we know this is going to be an elimination reaction, dehydrohalogenation, also called E2. And I've got my beta hydrogen here. So what I do is I make a diene. Here's another example. In this case, NBS in this alkene, I've got this allyl position. So this makes sense, but we also have this. We get a mixture of products in this case, right? And why is this? Well, obviously you can tell it's because of the resonance. So if I make this radical to begin with, that's resonance stabilized by this radical, right? And so if you do addition to, everybody calm down. If you do addition to this, one more time, to this position, you get this product. If you add to this position, you get this product, right? And so remember, resonance is describing both, or it describes one thing with two structures. So what it's saying is there's, it's going to behave as if there's a radical here and here. And then this gives us, I don't know if it's problems, but things to think about. What we have to do is think about all possible products. So if I do allylic bromination here, the first thing I want to do is identify the possible radicals, and then we'll think about them. So I could make this allyl radical, right? Or, this is kind of poorly designed, isn't it? Sorry. I could make this one. Then I also have to think about the resonance, because I'm not really making just one radical. I'm making the resonance stabilized radical, which is both of them. So that guy, right, that's going to go to the other position. All right, so these are the pairs of radicals that we're going to make. And neither one is more stable. They're all secondary allyl in this case. So neither one, there isn't one that's more stable than the other ones. If there were, we would use that pair of resonance structures, but not here. So in this case, we're going to get a mixture of products. We're going to get the bromine here. We're going to get the bromine here. The bromine here. And here. And I think that's the same as one of the other ones, isn't it? Let me put the look and let's see. Hold on. 1, 2, 3. Did I do something wrong? Okay, this guy's definitely different than that guy. This guy. Ah, these two are the same. Got it. He's the same as this guy. So 3 possible products here. Right? So you might get mixtures is the point. One more time, let's consider this guy. So how many allyl positions do I have? 2, right? So I can make this radical, or I could make this radical. Then I draw their resonance structures, right? Draw the allyl resonance. So we got this. So now we can identify, I think that we're going to see a difference here. So this one we call primary allyl. This one is secondary allyl. This one's secondary allyl, and this one's secondary allyl. So if you compare it, this pair of resonance structures, I'm air quoting right now, is more stable, and that's going to lead to the major product. So secondary is slightly more stable than primary. Tertiary, if you had a tertiary one in there at all, you're going to use that one. Tertiary radicals, tertiary carbocations are super stable. All right, so we're going to draw the products here. So these guys are going to lead to the major products. So I'm going to get this and this. All right. The most stable, this is terrible. Most stable radical will be the fastest formed, right? And we have to consider both resonance structures. Nice. All right. We'll talk about making alkyl halides from alcohols.